Today is Tuesday, November 6th, 2018, and we're continuing the NHERI SimCenter's Advances in Computational Modeling and Simulation webinar series with a question and answer session on deep learning with Professor Yu. Her prior webinar is posted on the SimCenter's YouTube channel, and you can get there from the SimCenter.DesignSafe-CI.org website, where you can find links to the NHERI Learning Center and the SimCenter's Knowledge Hub. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Computational Modeling and Simulation Center. This webinar is supported by the National Science Foundation under Awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. We're joined again by Stella Yu. She has a joint appointment in electrical engineering and computer science at UC Berkeley and at the International Computer Science Institute, headquartered at Berkeley, California. At ICSE, she directs the computer vision group, and on campus, she teaches machine learning and computer vision. Stella was brave enough to agree to a question and answer format for this webinar. We're going to start with a brief recap of machine learning from her prior webinar, and then relay questions that have been submitted previously. Again, if you have a question, please send it through the chat feature to the moderator or raise your hand to be unmuted. Participants will remain muted otherwise. Professor Yu, if you'd like to give us a brief recap.
Yeah, can everyone see the screen? Okay. In the last webinar, we went over 4 sections of materials. One is some deep learning applications done in my group. For example, the screening tool for classifying whether an image contains valid crystals. And we want this screening to be universal, regardless how the material is presented and what device is used. We talk about SimCenter project on build a deep learning model to turn building information model to structure analysis model automatically. And we talk about Samsung's project in simulating how radio frequency signal will attenuate depending on the materials used on the building facade. And for us, we accomplish this by looking at the street view images and perform material segmentation from a small annotated data set. And to allow the deployment to a large scale city level modeling, we use aerial images. So we can have the rough material mapping over a large area. And because we can detect glasses, we can give 3D building models, the windows that often lack in the commercially available products. We also talk about global dental projects where technicians need to spend a lot of time learning the expertise needed to design the missing crowns. And it's a tedious and a long manual design process, even with the help of computer-aided design software. And we started with 3D models in their data set. We turned it into images. And the first step is to learn from technicians on predicting the crown field image from the crown missing image. The middle column is our prediction, and the right column is the technician design. But we didn't stop there. We also learn from nature instead of technicians. We pretend a crown is missing by performing segmentation on the image, and we train a model to predict the natural crown from the input that misses this crown. Again, the middle is our prediction. The third step is actually to capture dynamics of the functionality dynamics, where the crown needs to support certain mobility with a sparse context between the top and the bottom jaws. And this is very hard for human to do. And with machine learning, using statistical feature as a characterization, we were able to design more functional crowns. I also give an example on eyelid health, meibomian gland diagnosis project. Humans can give ratings based on quantitative instructions, but we can learn the measure from annotated data, the eyelid area, the atrophy area. We calculate the ratio, and we can achieve much better accuracy than humans. We can even track individual gland, how it evolves, individual glands, how they evolve over the course of, across the subjects, across different times. So all these projects, they look very diverse, but they all require human expertise. And we need algorithm that can bootstrap and extrapolate. And through these examples, I want to illustrate that we need to think big with big data. We don't try to use machine learning to capture human expertise. We should formulate harder tasks for machine learning to strive for better solutions. And machine learning is about prediction, predicting Y from X. And we talk about the usual 6-step recipe. You first need to turn the data into a feature representation X and Y. And you need to choose a loss function that measures how well the model predicts Y. And you need to pick a family of functions that might predict Y from X. The proper experimental design need to look at your model and then go out and collect the right data. Model is also data, right? It's a re-representation of data. So the data are very important. Once you have data, you have your model, you can minimize the total loss over all the examples. And then you can evaluate the optimal model on the new data. The last step is equally important. And we show what deep learning is about. It's a series of compositional models. From the raw input data, you compute the features of the raw data, features of features of features. With this composition, you can learn so-called end-to-end, mapping the input to output. The output could be very abstract. For example, from image of a bike to a semantic label of bike. This is a pipeline for image classification, but in terms of what deep learning has been able to do, you can sort of put into different application scenarios. Another task will be semantic segmentation. You want to give each pixel in the image a label: cat pixel, grass pixel, tree pixel, or sky pixel. Or you don't just say this image contains a cat. You want to give a bounding box of where the cat is in that image. That's a detection, classification, localization task. The third thing is a detection. You have something in mind, you look for that instance. Can you detect every object that you're interested in? That's a detection task. Last one is instance segmentation. The difference is if two instances of the same semantic category show up next to each other, you should separate these as two different identities. That's what is not semantic segmentation would give you. It will just treat these are all cat pixels. It doesn't have understanding of one cat instance from another cat instance. So given all of these different application scenarios, in my group, I focus on several issues. And I point out one thing about misconception, common misconception. People think deep learning requires big data. There's a fine distinction between big data and big annotated data. When human experts are involved, you usually have big data, but you may not may not have big annotated data. I showed a work we have done that given just ImageNet images, we can learn the apparent visual similarity. And if I have some idea of the categories, our approach can take that semantic guidance into learning the proper feature. For example, this image, the last row shows the results when this particular image is given the label of dress. There are a bunch of other images labeled as dress. With that external guidance, what is considered similar changes drastically. It's not the same model wearing the dress. It's all the dresses sharing this puffy looks become more similar than others. We also talk about the SimCenter AI team is working on the BIM to SAM modeling, starting from JSON files for BIM and SAM. During training, we turn this into some feature representation and train a neural net to accomplish that, the mapping from BIM to SAM. Once we have the SAM, we can reconstruct the SAM in JSON format and put through this simulation software. We can measure the simulated response to the field shake data and get a sense of the quality of the model. With that, we can come back and remodel our neural net and output SAM model with a specific quality level. Last thing we talk about is BIM to SAM requires a lot of BIMs. How can we get a large scale BIM data set? Another line of effort is to extract BIM modeling from images, street view photos or satellite photos, all kinds of maps, cross-referenced data sets. For example, building footprints data set, building permits, land use. These all have GPS coordinates. They are cross-referenced. And here's an example where the building construction types are annotated already. And that becomes a relatively straightforward image classification problem. So that's what we covered last time. Matt,
thank you for that recap. So we're going to begin the question and answer portion. We have some questions that were submitted previously, and we'll begin with those, but I want to remind the participants that if you have a question, please send those either through the chat feature or raise your hand to relay your question directly. So Stella, the first question is, I have a question regarding the reduction of the high dimensionality of the outputs for a particular deep learning problem. It is known that PCA technique is usually utilized in this regards. Can you please explain to us the shortcomings of this method and what are other competing methods that can be used instead of PCA?
Okay, PCA stands for Principal Component Analysis. It is a common dimensionality reduction technique. It tries to maximally retain the variance in the data after the projection. It assumes that large variation in the data set correspond to variables we're interested in. Those variables contain information. The aspects, the dimensions that lack variation across the data set, they tend to be noise. If that kind of assumption fits your model, you can apply PCA. The problem with PCA is that when PCA is used on X, your input data, in the task of predicting Y from X's features that are relevant for Y could already be lost in the dimensionality reduction. It may have very small variations, so they can be thrown away because of the small variation when you do the projection. Since PCA is performed without looking at Y, you made a premature decision about what features are relevant for the model. Another major caveat of PCA is that it is highly sensitive to data scaling. if your data X contains different types of measurements, PCA would change drastically with the choices of units for these measurements. Canonical correlation analysis, so-called CCA, is an alternative choice. CCA assumes that both X and Y are generated through some common latent space, say C, and they may use different linear projection to generate Y and generate X. They may have some additional components which correspond to noise that added to either X or Y. Given such a generation process, CCA will be able to find the correlation between SY because they're fundamentally linked by some latent linear space. CCA is a linear approach. There are nonlinear extensions. There are also other nonlinear approaches. For example, in the deep learning era, there's this encoder-decoder type of neural networks for regression from X to Y, where the latent representation is chosen to be of a much smaller dimension. So you can think of, you have a big amount of data X. You go through something with a bottleneck. That bottleneck is the latent representation you're interested in. What you are saying is that although there are a lot of dimensions in the input, fundamentally all these can be represented with a small, much lower dimensional representation. For example, in MNIST digits, you have, let's say you have 50,000 images, but all of them are just different ways of writing 0 to 9. So the latent representation can be much smaller. How many variations you can write, how many different ways you can write 0 to 9. And so that latent representation goes through another few layers of processing. That portion is called a decoder. And so given the latent representation, which is much lower dimensional, I can synthesize, I can generate so-called decode. I can decode the latent representation and generate the image. So in this case, in this encoder-decoder type of networks, it can be understood as learning both dimensionality reduction and the regression automatically from the data themselves. Given a certain network architecture, you can think of X go through encoder becomes latent representation. L goes through a latent through this decoder network, and it generates your Y. That's the deep learning version of CCA.
Thank you. So the next question is, can you please give details about the BIM to SAM work that you've done, such as inputs and outputs, the neural nets and its layers? And where do we find the JSON file data?
Okay, I'm going to turn this over to Kai Gui, who works on this project. And he can go over the design flow as well as showing the script to give you a sense of how it's done in detailed TensorFlow code. So Matt, can you switch? Can you turn?
So Stella, you'll need to stop sharing.
Okay.
At the bottom.
Yeah.
And now Kai Gui can share.
Okay, can you see my screen?
We can. Do you want to put it in presenter mode? The PowerPoint. Yeah.
Okay. Can you hear me?
Yes, we can.
Okay. So next I will talk about our BIM to some project. This is the basic framework. So the input is a BIM file and the output is a SUM file. They both are JSON files. For the neural network, the input is a BIM feature vector and the output is a SUM feature. So the neural network doesn't deal with the raw data, the JSON files. So first, we need to estimate the BIM feature from BIM files. We call it encoding. And after we got the SUM feature, we can generate the SUM file. We call it decoding. So when a SUM file is given, we can use the SUM file as the input for the simulation analysis. For example, using OpenSys and compare with experimental results, we can estimate the model quality. As shown on the right-hand side, this part of work could be used as a tool to select the best SUM feature and also can used as a method to measure the quality of the SUM file. So here I show example. The left one is for BIM file, the visualization of a BIM model, and also a segment of its JSON file. The right one is the visualization of a SUM file in a chord mesh and the two segments of its JSON file. So first, to estimate the BIM feature, the left one is a BIM model. For each component, we can use a cuboid to represent it. So a cuboid could be represented by a vector, which including the information of its barycenter coordinates, its dimension, and also its material parameters. And then for each vector, we can project this vector to a higher dimension in a vector by multiply a random projection matrix. And in the end, we sum up these higher dimension vectors and do the normalization using cosine mapping. And finally, we got a BIM feature vector. For example, here, the dimension of our BIM feature is 512. Okay, for the SUM feature, it's including two kinds of information. One is material parameters, and the other is geometry parameters. So first, I'll talk about material parameters. So here, the left is the material parameter in a BIM file, and the right one are the material parameters in a SUM file. So we can find out some of the material parameters can be derived directly from the BIM file, but some of them which appear in the SUM file but never indicate in the BIM file. So we are focused on this kind of parameters, for example, data, AP, AN, and BN. And the analysis show that two of them, AP and BN, are much more important. So we here only focus on these two parameters, AP and BN. Another parameters are the geometry parameters. Here, for example, the number of chords in the middle part of the word around the horizontal direction. So here we show n equals 8, 10, and 16. But in our framework, we require the number of chords should be between 2 and 10. Okay, so next I talk about the data set. We have 51 words, and we're randomly choosing 10 as validation set and 10 as testing set, and the rest, we use the rest for training. Okay, for the SUM file, for each word, we have 64 combination of these 4 parameters, and also we have 9 types of meshes. So for each word, we have 576 SUM files, and then we need to choosing the best one. Then for each SUM file, we do the simulation and compare the simulation results with experimental results, and we choosing the best one. For example, here for one word, here I just show 8 comparison, the comparison of the experimental results and the simulation results. And for example, we can choose the best one based on the distance between the experimental and the experiment and the simulation results. And all of these data sets are public accessible as shown in this link. So if you are interested, I can send to you through email or by other ways. About the neural network, the goal is try to predict the material parameters and also the geometry parameters. We can formulate this problem by a nonlinear regression problem. So here in the TensorFlow, it can be written using only a few lines of code. And these are the some results. The red part are the best parameters selected from 576 sum files, and the black ones are our predicted results. We can find out some of them are quite close, and some of them are not so good. I think there's still a lot of room to improve the results once we have more data. And in the end, I show you two examples. These examples are the sum files generated based on the predicted parameters using our neural network. And we do the simulation and compare with experimental results. And this to show that they are quite close. It can used to show that our predictions are reasonable. And here is, I also show a little bit about the script I used to build the neural network. So here we do the data processing using other software, and we store the beam filter and sum filter here, FE and LV. And we separate the data set into training set and also the testing set. And here, this is our neural network regression model. And then in the end, we can predict the parameters using the testing set. Okay. That's it.
Okay, thank you, Kaikwei. Are there any maybe follow-up questions to that? If there are, you can send those to the chat or raise your hand. I wanted to point out where some of these data sets can be found. So let me share my screen. If we go to DesignSafe, that's DesignSafe-CI.org, and go to their data depot, the SimCenter's data is published in community data, SimCenter datasets, simulation and experimental datasets, and here are the wall collection, RC wall collection, University of Washington. So this is where the data is stored. So moving on to our next question, Stella.
Yes.
The next question is, as you know, there are many machine learning algorithms out there, and we have so many options to choose from when we want to develop a meta model. It is very important to choose the right algorithm in advance instead of trying a bunch of them and comparing their performance. I need to know how to choose which algorithm to use. In other words, which algorithms work better for which problems?
So maybe I can put the I can share my screen.
Go ahead.
Where is, okay. So first you need to decide what your X and Y, what kind of application scenario, what model you are building. Is it image classification problem? Are you making some, you have a bunch of data at the input end, you have some data at the output end. Is the output a summary, derived property of the entire input? If that's the case, it's a classification problem. And is your output discrete classes, representing discrete classes, or representing some numerical quantity? If it's numerical quantity, it can have continuous values, then it's a regression problem. And or you may, your data in the image case, the input is an image, the output could also be an image. That becomes a segmentation problem. Maybe you want the pixel-wise labeling of every pixel in the image. Unlike the first case of full image classification, you want to make one assertion about the entire image. Or is it a classification or localization problem? You want to classify what your input data is, and you know which portion of the data gives you that assertion. Or there may be the input data contains multiple instances of what you're interested in, and you want to detect all of them. That's a detection problem. So first to figure out the nature of your input and output, and then put them into these categories of formulations. And then for each category, you need to look at the type of data you have. Do you have a lot of training data? In your test scenario, are the test data sort of like your training data? For example, you have a warehouse, you have a lot of products. During training, you can take many pictures of the warehouse, every product you have. So that's a closed world learning problem. You can use the model to overfit to the training data. But in some cases, your training data is a small fraction of what you're gonna see during testing time. Then you want to choose an algorithm that actually generalizes better. You don't want any model that overfits. You may get a model that fits very well to your training data, but at the test time, it will be disaster. You figure out you understand your data, understand the task, and then you go look for what's the available techniques out there. If it's a full image classification, the usual network model you can start with maybe residual networks. There are many sophisticated versions out there, but ResNet seems to be performing pretty robustly and often gives you good results. There are also algorithms. There are research papers on selecting the right architecture. But so far, it remains in terms of the simple characterization of the knobs you can turn. For example, you can choose how many features per layer, and then you do some kind of optimization to figure out the right set of parameters. There's active research on that topic. For now, to get a sense whether deep learning can deliver for you, you can start with some default setup and tweak few parameters and just give a sense whether the performance is stable across different perturbation of your network architectures, or it's very sensitive to certain parameters. The good thing is a lot of deep learning approaches, they share the code online. And that's another thing you should take advantage of. Some methods may be sophisticated. If they don't have code available, it takes too much time for someone in applications to duplicate the algorithm. So it's much better to try something that actually works for your type of data, your type of task, and try it out and go from there. And I have done quite a few collaborative projects, and I think that this collaborative research model is a good model. For people working like structural engineering domain, it often, maybe you need a lot more background knowledge to catch up with the latest. You will be much better off if you can find someone in machine learning to work with you, to combine your expertise in the domain and in machine learning and deliver something quickly and optimally.
Okay, thank you, Stella. The next question, can I use machine learning to solve differential equations?
If you want to solve differential equations for the sake of solving that, those equations, there are packages for that. But machine learning can help you in few cases. For example, maybe it takes a very long time to solve your equations. But if you can, during training, you can generate such, initial state or boundary condition. That's your X. And there's some, at the end, you have some equilibrium or minimum energy state. That's your Y. And you can train a network to memorize the association from X to Y or from Y to X, this inverse modeling aspect. Deep learning can make this process much faster. In a way, it's a nonlinear, sophisticated lookup table. And especially in inverse modeling, that's a very useful technique to have. Some of our fingerprinting results reflect that methodology, that way of looking at this, learning the results associating two sets of observations. Each of them could be partial, but there's a strong laws of physics relating them. There's noise involved. Also, if I solve them directly, it may take a long time. So these are good applications using deep learning.
And another question, can we use data from wind tunnel tests to create surrogate models or data-driven models that are computationally efficient?
So I don't know the domain very well to make a very strong recommendation, but based on the description, this follows what I just said earlier. If you know you have some data, some measurements that related to the things you're interested in, during training, you can have access to the model parameters, property that you are interested in regarding the objects, regarding buildings or tunnels. You can learn such associations. How the quality, how good the deep learning can deliver for you depends on many factors. Whether you have access to enough data, whether your model is has large enough capacity to model the complicated relationships between your input and output. But I think the data-driven learning approach may deliver some surprisingly good results if in the past you have only been used to model-based, physics-based modeling.
Okay. How detailed should input data be for training neural nets? For example, the bin to SAM example. as kind of a follow-up, you have mentioned dimensionality reduction for inputs and or outputs, which is useful if some inputs are not very relevant, but can you detect if the inputs are not relevant enough? For example, input X is not sufficient to detect output Y.
Mm-hmm. Yeah, that's a very good question. So I'm gonna answer along few lines of reasoning. One is that with respect to all these applications, you can use so-called raw data. And with this, in deep learning, so-called end-to-end learning, you don't worry about the representation. That's all the data you have at input and output. In the BIM to SAM, maybe just the JSON file. I don't want to think about representation. I'm just gonna take this JSON file for BIM and output the JSON file for SAM. That's not the approach we took in this case, because we know there are a lot of, it's very rigid text format. There are a lot of information we know is irrelevant. But potentially you can use that, the raw data representation. If you choose raw data representation, you need to make sure that you have enough data so the learning can take effect and rule out some superfluous connections between input and output. The second way of domain application is to use curated data, right? You come up with a list of features. This is done through domain experts. Their expertise, you know what features will be relevant. Some features, you know they're not relevant for the output. And so you start with these raw features, but the raw features, the curated raw features, you know they are good candidates for predicting why. The good thing is about this approach is that because you're using minimal set, the model needed would be very lean, a lean model, small model can do that. You have less chance of overfitting. The bad side of this is you may leave out some features which are helpful for predicting why. You just don't know it yet. So the performance may be subpar. So the third thing is what learning can do for you. If you already started with either raw data and curated data, what can be done through general learning approaches? In the old days, if you have too many features, you can use dimensionality reduction to reduce the redundancy. And that has a few benefits. You can, the computation is more efficient. The generalization may be better. And if you don't have enough features, meaning that if you have a minimum set of features, you want to predict why. And the classify learn, maybe you are looking at, say, linear families. And in this small set of features, you choose a linear model don't fit too well. What you can do is to do feature augmentation or feature lifting. You can use polynomial features derived from the given feature, or you can use kernel methods. So it's a way to perform classification, even linear classification, but in the equivalent lifted feature space through this kernel trick. Or you can use random projections to create much more features for the classifier to look at. Nowadays, with deep learning, this is really the major benefit of deep learning. The features no longer need to be engineered, no longer need to be handcrafted. It can be learned if you have a lot of data. So how do you get this trick? You don't get anything for free. The thing is you have to choose network architectures. Your choice of network architecture will have a big impact on what kind of features can be learned. In the encoder decoder type of networks I mentioned, if you use a bottleneck too small, essentially you assume that the intrinsic variation of the data set is very small. So you essentially impose a large regularization you assume that all the variation you are seeing, most of them irrelevant, only a few things are intrinsic. If you choose a big latent representation, then it can represent much more variation. Like, you know, if you have different ways of writing one, then even the subtle distinctions can be captured with a distinctive representation in that latent space. While if you choose a smaller bottleneck, then all these variation will be considered noise. It will be represented only with one point in that feature space. So these are, you know, regarding how do you know you have the right X and the right Y? I think it takes a combination of skills. One is your familiarity with the model, say deep learning architecture, learning tools, the problem itself from domain expertise, what is relevant, what is not relevant. And experimentally, you can test it by cross-validation. You split the data into training, validation, and testing. You use the training and the validation set to tune your model. Once the model is, you optimize the model, you get your optimal model, you test on the data that is withheld during training. The model never seen such data, and you look at the performance. Sometimes if the model, the neural network model is too simple, then the performance on the training data will already be low. The performance will be poor because your model doesn't have the large capacity to capture the association between the input and output. If the model can do well on the training data, but test poorly on the withheld data, then it could be that you could be overfitting the training data, and when the test data is slightly different from your training data, the model just cannot generalize. So it takes some back and forth. It's not a static one-step process. You have to look at the multiple aspects together.
Okay. Maybe we have time for 2 more questions. The first one is, what information can be learned or inferred about buildings or maybe the built environment that's relevant to hazard and risk assessment from, I guess that is referring to images, so images to building information models. Is there information other than just the structural components that might be relevant to hazard or risk assessment?
Actually, I think there's a peer competition, right? Based on images, you can directly classify the extent of damage. There are a lot of efforts on that. If you want to, instead of going through a structural analysis model, you want to understand, you want to have an assessment of the damage. There's a lot can be done. You know, the size of a crack, the you know, different classes of damages. And I think Peer Center at the Peer Hub ImageNet Challenge 2018, there's already such problems out there in terms of scene classification, damage check, spalling condition, material types, collapse check, component type, beam, column, wall, damage level, no damage, minor damage, moderate damage, or heavy damage. Yeah, I think there a lot can be done deriving from images or other related data.
Okay. And maybe one last question. What is the difference between surrogate models and deep learning algorithms in terms of performance?
What does that mean, actually?
Okay. there's maybe an example is a Kriging model. So you develop a surrogate model that is a simplified model or a representative model that's used instead of a true computationally intensive model.
Oh, yeah. So there's a line called, all models are wrong, but some are useful. I think that all the models reflect some simplification, give away a piece of truth. Some models are better than others, and it's not an excuse to for sloppy models. And even our work on BIM to SAM models, we are striving for better performance, better prediction performance, even with the very small annotated data. Yeah, so surrogate models can be helpful in terms of computation efficiency, and whether it's during training or testing. Sometimes actually, test time efficiency is what you are striving for. Yeah, it's like any models. No models are perfect, but the data-driven deep learning models are very versatile. And I think the major benefit is you can get away with feature engineering.
Okay. Thank you, Stella, very much. We're at the conclusion of today's SimCenter webinar covering the advances in computational modeling and simulation. On behalf of the attendees, thank you very much, Professor Yu, for taking the time to answer our questions. To the attendees, thank you for your questions. I'd like to encourage you to register for future webinars and other upcoming NHERI events, such as experimental facility user workshops, and these can be found on DesignSafe's Learning Center webpage. Please check the SimCenter website at simcenter.designsafe-ci.org and check your inbox for emails from announce@DesignSafe-CI that will have registration links for additional upcoming SimCenter webinars. Thank you for attending today's webinar. Again, thank you, Professor Yu, for sharing your time with us.
Thank you, Matt.